Hello, everyone, and welcome back. In the previous video, we introduced first-order differential equations. And in particular, we talked about initial value problems, where you try to pin down a solution to those equations by being given a specific point that the solution has to go through. Now, we saw that we can get a little bit of information from these things using slope fields. And in particular, we have online plotters that can give us a nice slope field so that we don't have to sort of draw it all out by hand. What I'm going to talk about in today's lecture is how we can approximate the solutions to these initial value problems using what's called Euler's method. So let's go ahead and let's jump right in. Now, remember that a first order differential equation is written like this. Derivative is equal to some function of x and y. Now, also we know that if we have a solution, say y is equal to y of x, sort of rewriting this, but just to emphasize that we have an actual function y of x that will satisfy this, we can write it like this. This is a whole function of x. The left-hand side is a function of x. The right-hand side is a function of x. It's just a weird-looking sort of composition. Well, now we can use the fundamental theorem of calculus to undo the left-hand side. So if I integrate, let's imagine, say, we're given y of x0 is equal to y0. Let's integrate this thing from x0 to some point b that's beyond it, okay? And here I get d dx y of x, and this is equal to x0 to b of f of x y of x dx. All right, so all I did is I hit both sides with an integral. Now from the fundamental theorem of calculus, this tells me that I'm integrating the derivative. So this is just equal to the function evaluated at the endpoints, which is equal to, again, the right-hand side doesn't change. It's just integrating some function of x. And to do this, you're sort of assuming you know what y is, right? And that's an a priori assumption because, again, we don't know what y is. That's the whole purpose of doing this. So bear with me for a moment. But this tells me that I can find the y of b, so the value of y in the future, just by knowing where I've started and by computing this integral. Here's the idea. We're going to basically go back to a Riemann sum. So let's imagine, typically we call it h for step size. Let h be small. And set b is equal to x0 plus h. So I don't even want to go that far. I just want to know what the function looks like, one tiny little step further. Well, in this case, I get y of x0 plus h, the next point. This is where you started, plus an integral over barely anything at all. Now, if you think about this integral, this is super small. It is so small that it's basically just a rectangle. The function is basically a constant inside of this thing. It's the same principle as using a Riemann sum. You could also think of this as maybe approximating the integral by a single rectangle, by a single piece of a Riemann sum. And you're going to make that assumption because h is so small. That's your delta x, as we've been calling it. I'm using h here because this is sort of more standard notation. But that tells me that I can approximate this integral with a single rectangle. The width of that rectangle is h. That's x0 plus h minus x0. And the height of that thing is given by f of x0, comma, y of x0. So if you want me to draw this for a second, maybe I've got, I've been using red here. I've got this thing, and I'm exaggerating what it looks like for effect here, but I've got an approximation single rectangle from x0 to x0 plus h. And so here's the point, x0, comma, y of x0 on the curve y of x.
Okay.
So I'm just approximating the area under the curve using just one single rectangle here. But essentially what that tells me is that I can get myself h units away from where I started just by knowing what's happening at x0. So then, let's say if we set x1 equal to x0 plus h, then we can repeat well, if we want to go 2 units away, so x0 plus 2h, which is the same as going x1 plus h, so just another little tiny h away. You can repeat that argument that I just made above, and this would be y of x1. So you're using your x1 as your lower limit of integration now, plus h f of x1, y of x1. And you know all of these points on the right-hand side here because you've computed them in the previous step. So you can continue this procedure.
Fine. Let's say
xn is equal to x0 plus n times h. So you're getting n steps away by little h's. It's basically the reverse of a Riemann sum, so don't lose sight of that. And let's call y sub n equal to y of xn.
then you get this
Iterative scheme, yn is equal to, yn plus 1, the next one. So maybe I should make that nice and clear. You can get the next point forward by just knowing what's happening at the current point and adding this little slope piece to it.
So this is
right here what's called Euler's method. Approximation, sorry.
This is called Euler's method. It gives you an
approximation of what the solution to that differential equation should be if you sort of advance forward using this scheme.
So another way
you can see this is if you take your derivative of your function, say d by dx, y of x at n, so at your current step, this by definition is equal to the limit as h goes to 0 of y of xn plus h minus y of xn divided by h. Now, we can't do limits numerically. So what we can say is we can take h small, tells me that the derivative here, y of xn, this is approximately equal to this relationship because this is true in the limit. So if I take h really small, I'm actually approaching this. Now, the left-hand side is just f of xn, y of xn. And so this piece right here on the right-hand side becomes xn plus 1. That's what we just saw. The definition of xn plus 1 is h more than xn minus y of xn divided by h. And so if you rearrange this whole thing, you get the same relationship. That you get this relationship,
which is
exactly the Euler method.
So you can see
this coming from, if you wanted to, integrals using the fundamental theorem of calculus, or you can see this coming from derivatives using just an approximation of the derivative. So this allows us, particularly using computers, which I'll show in an example in a few moments, how we can approximate these solutions, because this gives me an approximate value of y at each point x in space. Now, we can just do this by hand if we wanted to. So let's start by doing that so we can see what's actually happening here. Sorry. So let's say find the first three approximations y1, y2, and y3 using Euler's method. For the initial value problem, so IVP, remember that's initial value problem, and we are going to be given y prime is equal to 1 plus y, with the initial condition y of 0 is equal to 1. And we're going to start at x of 0 is equal to 0 with h equal to 0.1. So now what we can do is we can set up this iterative scheme. So we can find y1 knowing what y0 was. We can find y2 knowing what y1 was, and we can find y3 knowing what y2 was. So let me illustrate here. So the first, so that's y1. This is equal to y0 plus hf of x0, y0. Now, the first thing that we have to ask ourselves is, what is f? Well, f is the whole right-hand side of the differential equation. So in our case, this is 1 plus y. So here we get y0 plus h times 1 plus y0. And now we ask ourselves, what was y0? Well, that is y at the initial point, 0. So this is equal to 1. So I get 1 plus, now putting in h is 0.1, 1 plus 1. And so I get 1 plus 1 is 2. 2 times 0.1 is 0.2. And then plus 1 here is 1.2. So we've advanced from 0 to 0.1. So we did one step into the future. Okay, now let's look at the second step. The second step here tells us that y2 is equal to y1 plus hf of x1, y1, which is equal to y1. So I'll put that in right away. 1.2 plus h, that's 0.1. And we said f was 1 plus y1. So maybe I'll just write it first just so that we can see it. And so here now I get 1.2 plus 0.1 times 1 plus 1.2. And here you might have to crack out your calculator. You get 1.42. And let's look at finally the third one. You can see already the calculations are becoming slightly tedious, probably necessitating a calculator. So I get the following relationship. So I skipped putting the f in there. I just put in the right-hand side of the differential equation. This is 1 plus y2 now. y3 depends on y2. And so I get 1.42 plus 0.1 times 1 plus 1.42. And so again, this is just a tedious thing for a calculator to do. So 1.662. So that gives me the first three approximations of my function or of my solution, my particular solution in particular, that goes through 0 and the point 1 for y. As a solution to this, y prime is equal to 1 plus y. Now, if I wanted to, I could easily compute the fourth as well, and I could compute the fifth and the sixth, and I can keep going forever, right? But this is just a really tedious thing to do. It's a lot of computations that are just annoying for me personally, but they really wouldn't be that hard for a calculator. And what better calculator than the one that you're watching this on, a computer, right? A computer is just a big calculator. It's running, thousands or millions of computations per second. And so what we can do is we can set up a recursive algorithm here. You can set up a nice little for loop that says, if you know what's happening at 1, then you can know what's happening at 2. If you know what's happening at 2, then you can know what's happening at 3, and so on and so forth. And you can just iterate through with these Euler methods. So to illustrate this, I am going to simulate, or I'm going to use these Euler methods to approximate the solution to this differential equation. So y prime is equal to 1 plus y, from x equal to 0 all the way up to x equal to 1 using different values of h. And I want to show you how this affects things. So what I did is I coded up a very simple little script in MATLAB. And what I'm going to do is I'm going to use two values of h. So I call them dx in the script here. And so the first one is using h is equal to 0.1. That's the one that we used on the previous in the previous example. I'm also going to try taking half of that. I'm going to take a slightly smaller step, and this step is going to be 0.05. Now I am going to figure out what my solution, or approximate my solution, from x equal to 0 all the way forward to x equal to 1. Now the nice thing about this differential equation is I know the exact answer, and that exact answer is equal to 2x minus 1. So I am going to compare what my approximations look like compared to my actual solution here. And the way that I implement the Euler method here is just with these little steppers. You can see that the next, the yn plus 1 is equal to yn plus h times the right-hand side of the differential equation. If you've never used MATLAB before, that's okay. That's not the purpose of this. I'm not going to force you to code something up, but the purpose here is just to illustrate to you, that we can get computers to do this much more efficiently than me doing it with pen and paper. Okay, so let me show you what the result is. We get two solutions coming out of this. Are two figures. So let's start with this one first, figure 1. So what are we looking at in figure 1? Well, you can see from the legend here that the blue curve is the exact solution. That's 2x minus 1. Then the red curve, a little bit further away from the blue curve, is the solution with dx, or h, equal to 0.1. And the green curve is the solution with h, your step size, or dx, equal to 0.05. Now, everything starts at 0, 1. When x is equal to 0, y is equal to 1. Everybody starts with that initial condition because that's what was given for the initial value problem. But what you can see is that as you get further from where you started, you start to stray a little bit from the exact solution, right? And in particular, you can see that the case where you have a smaller step size, it actually is a better approximation. And that comes to the fact that you're not jumping too far ahead each time. You're taking smaller little jumps. It's exactly the same principle that makes Riemann sums work as well. Remember, Riemann sums work in the limit. And so if you take smaller and smaller values of delta x, dx, h, whatever you want to use for all of these quantities, you get better approximations. Same thing happens here. If you take a smaller step size, you get a better approximation. And so just so we can see, how do we know which one actually is a better approximation? Well, what I did is I plotted in the next figure window, the error here. So basically it's going to take the exact solution and subtract off the approximate solution. So the distance from the blue curve to the green curve and the distance from the blue curve to the red curve is going to be my error. And so here's what I'm showing. Again, they're color coded in exactly the same way. The green curve here is with the smaller step size, and you can see that the error is smaller. The error always is below what happens when you take a larger step size. In particular, by the time you're all the way to x equal to 1, you've got an error of about 1/4 that's built up. Now that's actually quite big, right? An error of 0.25, you're off by 0.25. Whereas with the smaller step size, you are somewhere around 0.13. So you're about half of the error that you were getting when you were using double the step size. And let me illustrate this a little further. Let's go out even farther. Let's go out to x equal to 5. So we're going to simulate from x equal to 0 to x equal to 5 here. Let's run it. Just wait for it to compute. And in this case, again, the curves look more or less the same. Again, the smaller step size gives a better approximation. But really, the only thing that changed is the y-axis here. So this distance, although it looks the same as when the x-axis was down there, went from 0 to 1, it is much larger. And that comes from the fact that the y-axis is much more stretched. And this is immediately apparent by looking at the errors as well. So by the time you get all the way to x equal to 5, your error for the smallest step size, you're off by about 33. Remember, going up to 1, you were off by about 0.13 or something like that. Now you're off by 33 point something. And for the larger step size here, you're off by about 62. So you're really, really far off. And the reason for this is because errors accumulate. Remember, you have an error going from x0 up to x1. That came from approximating your integral with a single rectangle. So, okay, now you're using x1 to find x2, but there was a problem with x1, so that's going to carry over to x2, plus you're doing new approximations to get x2. So now you have double the errors on x2, or on y2. Okay, now to get y3, you've got errors from using y2, and you've got new errors by approximating your integral again. So now you have triple the errors. And similarly, you can keep going up. So to get y100, you need to use y99, which has all kinds of problems already built into it. And then you need to put another slight error into it, another problem piece, in order to get y100. So you can see this, you get a percolation of errors that slowly build up. And the further you go in x, the worse and worse these errors are going to be. And that is immediately apparent from this figure right here. So let me illustrate it one last time. Let's go all the way up to x equal to 10. So in this case, let's see what we've got. Now we can see that the errors are just awful, right? Even for the smaller step size, we're off by 9,467 units, right? So if we wanted to get a good approximation all the way up to x equal to 10, we would need a very, 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 very small step size. So that's what I want to close with. I want to show you how much better you can do if you choose an even smaller step. So let's go up to x equal to 5 here again. And let's use a step size of, let's say, 10 to the minus 2. So 1/5 of what we used the first time. Let's just update this so we can see it in our legends. And let's run this now. It'll take slightly longer. But now what you can see is that the error is much better. So the error in this case, when it was about 33, now we've brought the error down to about 7. And I didn't change the red curve at all, so nothing is new here. So we're only looking at the green curve in this picture. And in particular, you can see, your approximation almost lies right on top of it based on this figure here. And that comes from the fact that we're using a slightly smaller step size, so we have a much better approximation. And the final thing that I'll do is I'll bring that down an entire order of magnitude again, 10 to the minus 3 now, and we'll see how much better our approximation is. Now you can see that the green curve is almost completely flat. The total error is about 0.7. Remember, when we used 0.05 as the step size here, the error was like 33. So we brought it way, way, way down by using a smaller step size. And you can see it as well on here. It's almost impossible to distinguish the blue and the green curves. Our approximate solution with a super small step size is basically the exact solution. If I zoom right in here, now you can see some distinction between these two things, but it is very, very, very small. Okay, so that's just a little demonstration of how you can implement these things numerically on a computer. And of course, when you're using a computer, this comes at a cost. If you are going to use a very, very small step size, yes, you will get a better error, but it takes longer to run the program because you're not going forward very far, right? If you're starting at 0 and you're taking steps of 0.1, it only takes 10 steps to get to x equal to 1. If you're using a step size of 0.01, it's going to take 100 steps. So that's 100 iterations through your loop. If you're using a step size like our last example of 10 to the minus 3, it's going to take 1,000 steps to get to the end. That's 1,000 computations, at least, that your computer needs to run to get to the same place where the smaller step size of 0.1 did it in 10 steps. So, you could take one thing away from this and say, well, just always use a super small step size. You get an incredibly accurate approximation. But when you start doing this for more complex differential equations, that's not always feasible. It could slow your computer down to a complete crawl, and it could take, days or weeks or even years to just run a simple computation because there's so much that needs to be done in the background by the computer. And this is a big thing that people think about in mathematics. They think, how can I trade off accuracy, so use a slightly bigger step size, to make this thing run faster, right? I'm only so young for so long. I don't have infinite time to wait around to let a computer program run. In fact, I don't really want to let something run for more than even a day. So I need to think about, what is the accuracy that I'm willing to live with in order to get a good enough approximation that it runs in an accurate time. And this is all intertwined with what we've already talked about with integrals. We saw these approximations of integrals using the trapezoidal and Simpson's rule, and we found these precise error computations that told us, if I want to accurately approximate this integral up to some prescribed error, so I think we use 10 to the minus 4 as an example, then I can figure out how many discretizations that I need to use here. I have similar formulas using the Euler method to approximate differential equations. I can say, if I want to approximate the differential equation up to an error of 10 to the minus 4 again, I can figure out how small my step size has to be. And in that, I can figure out how long that program is going to take to run. So there's a massive trade-off here that you can play with by programming up your own examples.